All right, so we have exam 2 on Friday. That's the 4th. And for us, did I say what topics it was going to cover? No. Okay, right. No internal loads. So the topics are through stresses in objects loaded like stress elements. So that's no internal loads. And the stuff that we're doing now is internal loads. The next thing that we have to do related to internal loads is talk about how to do internal loads calculations if you have distributed loads on the members. So I'd be happy today and or Wednesday to answer questions related to the test. So if you have any homework questions or anything like that today, or if you want to bring them Wednesday, I'd be happy to go through them. Any questions right now? I don't know. If I did, yeah, if I did know the answers, I'm sure I would have given them to you. No, right now I would have just handed them out, but oh well.
Can you repeat the entirety of Friday's lecture so it wasn't like I wasn't coming?
I don't know. That seems like maybe that's not the best.
Good for me.
What?
Do it all at 1.5 speed.
Is that how you watch those videos? 1.5 speed. Smart. That's the only reason they do it. Okay, so let's keep going with internal loads then. So far, we've only covered internal loads in beams subjected to point loads. So now we have to go into distributed loads. Yeah.
So when you say through stresses and objects loaded like stress elements?
Yeah.
Just they're loaded like stress elements, unlike
Okay, so let me give you an example of one that would be and one that wouldn't be. Watch this. You know what I'm going to do after I'm done with this? Paste it back in there. Okay, so here's an object loaded like a stress element. So if you have any kind of distributed load along the face like this, it has to have the matching distributed loads Okay, and these have to be the right values for this to be in equilibrium. And then, you could have,
So are those on?
So it's like movements.
what?
The box folded out kind of
No, that is,
distributed.
this is just a bar, Sure, a beam. It's not really a beam because a beam requires transverse, it requires loading perpendicular to the long axis. But yeah, it's a long, slender thing, body.
You can just stick to your joke.
But the key is that all of the external loads applied to it occur in the places that they would have to for this to be a stress element, to have a symmetric stress tensor. So like this, whatever this is, 10 newtons per meter squared up here, this has to be 10 newtons per meter squared going the opposite direction. This one has to be 10 newtons per meter squared. That's a pretty low. I don't know why I chose 10. That's a really tiny force, but 10 newtons per meter squared like that. And then this has to match the other one. So let's say this is 50. So this is loaded like a stress element because every load on one face is matched by an equal and opposite load on the opposite face, and any of these shear distributed loads have 4 faces in the pattern that's required for a stress element.
Do all those tens? Do those all have to be the same?
They have to be the same as a distributed load. But there are problems where I'll give them to you in newtons, and then they wouldn't be the same because, the areas are different. You need those tractions to be the same, not the total forces. And then here's one that isn't. So let's say same member. But this time you have a load that way and a load this way. Say these are the same. This object could perfectly well be in equilibrium, and you have a 20 going to the right on the top, a 20 going to the left on the bottom. But this one, we can't just go directly from this to the stress because this is missing the distributed loads here and here that would make this an allowable shear pattern for a stress element. Okay, so this we can calculate, this we can't yet.
So, and a stress tensor, like the shear stresses like this have to be the same, right?
Right.
But in this case, depending on the surface area, they won't be the same.
No, it's those. Remember, those stresses are per surface area.
Oh, Pascal. Okay.
Yeah, right. So, so you're right that as total forces, that's what I was just saying, that the total force here is different than total force here. But if you write it as newtons per meter squared, then they have to be the same.
Wouldn't a good example be like both the arrows going the same way on that, and then like the rest would have to compensate even more?
That would be, yeah, that would be another, I mean, good is subjective. That would be an example. Yeah, that would be a different example. Wouldn't a better example. That's what you meant. That's why I didn't like that. Any other questions about that? Okay. Okay. It's time. Force, the force. If the force is strong, if you have the force strongly enough in your midichlorians, you can do that in your notebook right now. I don't know, we were just watching a Star Wars movie this weekend. That's the thing in your blood that gives you the power of the force. You can measure it with like a blood test. No. No. Yeah, that's a very good question. They never addressed that. It's like blood doping. It was a long time ago. Okay, so the key thing that we're going to do with distributed loads, to do calculations involving distributed loads, calculations with distributed loads, we're going to have to go from the distributed load to representing it as a point load. And that means two things. First, we have to figure out what the magnitude of the point load is. For us, it's always going to be a point force. Well, sorry. So we're going to have to calculate the force vector for the point load. And second, we're going to have to calculate where that point load is applied. The location where that force vector is applied. So if you have a distributed load like this, the total force vector comes from the area of the distributed load shape. So let me put some numbers on this. Let's say that this has a length of 3 meters. And at its highest point, this distributed load is 10,000 newtons per meter. Then the total force is just the area of this triangle. Very good. You're going to do great on the PSAT. So 15,000 newtons. The direction is just the direction of the, these are always going to be going in the same direction. So in this case, it's down. And the location of the point force, is the centroid of the shape. Okay, so I have to, so the centroid is there, and that's where that force is going to be applied. So let me give you some information about some common shapes, and I'll post this PDF on D2L too. What? What's 2 meters? Oh yeah, 2 meters, yes. Sorry, I didn't even do that. That's right. Okay, so centroids and areas of common shapes. So the first one is a right triangle. So if this is B, this is H, and there's the centroid. So I'll call this X bar and this Y bar. Then the area is equal to base times height over 2. X bar is equal to base over 3. And Y bar is equal to H over 3. Second one is a quarter circle. And for this one, we're assuming it has a radius r. And the centroid is here, and we'll measure X bar from the center of what would be the circle, and Y bar is from the center. Then the area of this shape is pi r squared over 4. And X bar and Y bar are both the same. They are equal to 4r over 3 pi. And then the last one I'll do is a parabolic shape. So the rest of the parabola would go this way. this. So here is the centroid. And I'll call this X bar and Y bar. The area is 2 times A times H. Oh, I didn't tell you what those mean. So A is this. And H is this. So why is H horizontal? Because I laid this down on the side, because for our purposes this will be the direction that we care about. And so like if you use this PDF that I'm putting on D2L, the meanings of X and Y are sort of flip-flop, but you can get that from, you can understand that from just looking at the pictures. Okay, so the area is 2AH over 3. X bar is 3H over 5. And Y bar is 3A over 8.
Is this an ellipse or is it like a parabola?
It's a parabola. Do you need what? Do you need a pi? No, not with a parabola. It's going to be great. Okay, so those are the ones we're going to use. All right, so let's do an example of an external load. So let's say we have a cantilever beam with a triangular distributed load acting. Say that's 1/2 meter. And this is 5,000 newtons per meter. What are the reaction loads at the wall? So free body diagram of the beam. I guess on this one, let's neglect the weight. Okay, so what's acting? At the wall, that's a fixed joint, so there's a force vector and a couple. And then there's the distributed load. If we treat that as a point force, it's going to act. So with right triangles, whether you're looking at it horizontally or vertically, you can think of there's always like a wall side and a point side. Okay, and the centroid is always closer to the wall side 1/3 of the way across. So depending on which way you're going, which way you're counting, it's going to be, you know, these distances are going to be 2/3 of this distance, 2/3 of the length from the wall over to here, or 1/3 of the length from the tall side of the triangle, the wall side of the triangle. Okay, so it's going to be acting there. The total force is 5,000 times 0.5 over 2. And so that's 1250 newtons. And so Newton's second law says we have a force of 0, negative 1250, plus Rx, Ry is equal to 0. And so the reaction force is 0, positive 1250. And now for the moment equation, we have to choose an about point. Let's choose it about where the interaction with the wall. So on the right end of the beam. Okay, so what's the moment produced by the force R? 0. Yep, any force at the about point produces 0 moment. What's the moment produced by MR? MR. And what's the moment arm for this 1250 force? 2/3 times the length. Yeah. So 2/3. 1/3. So that's 1/3 times 1250. And then would that force, if this is the about point, if you imagine a hinge at the wall, would that force produce a clockwise or counterclockwise rotation? Counter, so this is positive. And that's equal to 0. So what do you get for MR?
416.67.
Negative 416.67 Newton meters. For distributed loads, when you're doing cuts, when you're using distributed loads for internal loads calculations, all the same rules hold. But you're often going to have to use functions of x in your expressions. So you'll often have functions of x in your expressions for the area and the centroid location. So in each cut, where the cut is inside a distributed load, here's what you're going to need to do. First, you're going to have to represent the height of the distributed load as a function of x. And then use that function from step 1 as the height of the distributed load at the right end of the cut. Okay, so let me give an example. And let's use the one that we just had. Okay, so we have a 1/2 meter long beam with a distributed load of 5,000. Oh no, I don't want to do that one. No. Let's use a different one. Okay, so we have a beam here. Yeah. Okay, so let's say that this is 2 meters long. And let's say that this is 4,000 newtons per meter. And let's say that we already know these. It turns out when we do the cuts, these won't affect anything anyways. Okay, so how many candidates are there for what? Yeah, right. Yep. So how many candidates are there for places where those subfunctions are going to change? Yeah, just the endpoints, because it's the same distributed load the whole way across. And so this cut has to represent, there's only going to be one cut because we have 2 of those points. 2 minus 1 is 1 cut. And so this has to represent all x values between 0 and 2. Okay, so here's our piece. Here's the piece that we're leaving off. Here's the distributed load. Here's the part of the distributed load we're leaving off. The forces at the wall are over here, so those aren't going to come up in our calculation. We have the internal loads, tension, bending moment. Whoops. That was the shear force. Tension, shear force, bending moment, and then torsion. And so now we have to, in order to go on with this calculation, we have to represent this part of the distributed load as a point force. So the first thing we have to do is come up with a function of x to represent the height of this distributed load at any value of x. So we need the line function, So we need the equation for the line that represents this distributed load. Yeah.
Does X always start at the left?
Yes, it always starts to the left. I mean, if you cut the other way, then you'd probably want X to start at the other side, but let's just not ever do that. It's not like conceptually hard or anything, just always do it the same. Then you won't make mistakes. So yeah, for us, X is always 0 at the left endpoint. All right, so so if this is X equals 0, and Y is equal to 0, and this is X equals 2, and Y is equal to 4,000, what's the function for that line? Right. So it's a rise of 4,000, a run of 2, so the slope is 2,000. The y-intercept is 0. So I'll write it as 4,000 over 2 times x plus 0. So 2,000x. And so that says, over here, the value of that distributed load is 4,000. So what's the value of that distributed load here when we're x away from the left endpoint? Yeah, so the height at this point is 2,000x. And so now the force magnitude, the point force magnitude, and point force location come from the area and centroid of this shape. It's a right triangle where this is x and this height is 2,000x. And so A is equal to 2,000x times x over 2, so 1,000x squared. And the centroid what's this distance? Yep. Anybody have any questions about that? Okay, so now we can redraw the free body diagram with that distributed load represented as a point force. So we have this downward force, that's this function of x, 1,000x squared. And this distance is 2x over 3. And then we have our internal loads, T, V, M, and torque. And now that we have it represented as a point force, we can go to Newton's laws. So Newton's second law says 0, negative 1,000x squared plus T0 plus 0, negative v is equal to zeros. So tension is 0. Shear force is negative 1,000 x squared. Now we can do our moment equation about the x-axis. There's nothing going on along the x-axis. None of these produce any torques about the x-axis. So we just have 0 plus t, 0 plus fancy t is equal to 0. So fancy t is 0 the whole way. And then the moment equation about the z-axis. The moment arm for this 1,000 x squared is 2x over 3. So we have 2x over 3 times 1,000 x squared. And would that force produce a clockwise or counterclockwise moment about that left endpoint? Clockwise, so this is 0. This is negative. Any questions about that one? And then the other things that produce a moment about the z-axis are just adding on that couple m, and then the minus vx that we always see. So you get m is equal to Vx plus 2,000 over 3. So that's like 666 x cubed. And now you have to substitute in for v. We know what v is. So this says negative 1,000 x squared times another x plus 666.67 x cubed is equal to minus 333 x cubed. Any questions about that? Okay, let's stop there. I'll just go through more examples on Wednesday. And if you have any questions about homework or whatever, bring them on Wednesday and I'll answer those to get ready for the test.
So the quiz on Wednesday will be anything from last Wednesday to
Right, through today.
Wednesday, Friday.
Yeah.